Okay, this is still section 4.4, and we're going to talk about two really important theorems in this section. And this first one, the mean value theorem for integrals, is what leads us up to one of the very important theorems called the average value theorem. So, or the definition of average value. So, mean value theorem, I'm going to read it to you and try to explain to you what it means. It says if f is continuous on the closed interval from a to b, then there exists a number c in the closed interval from a to b such that the integral from a to b of f of x dx equals f of c times b minus a. Okay, so first of all, let me kind of explain to you what that means. When we started first doing area under the curve, okay, this is saying I have a closed interval from a to b. So here's my closed interval. I can use a rectangle to try to estimate the area under that curve. This is an LRAM, or the left-hand side of my rectangle is touching. This is also called an inscribed rectangle, and the area of this rectangle is going to be an underestimate of the actual area under that curve. Again, if I have that same closed interval from A to B, but this time I use a circumscribed rectangle, or RRAM, this is going to give me an overestimate of that integral from a to b. Okay, so what the mean value theorem for integrals says is I am guaranteed some number c. I'm not sure what it is, but it has to be between a and b such that I get a rectangle, I'm going to say that that's point C, that gives me the exact value under that curve. Okay, so the mean value theorem for integrals helps you find out what that C value is. And we're going to find it by using this right here. Okay, so let me show you what it would look like in your homework. I know this example is not in your notes, so you'll need to write it down someplace. I think this is actually number 45 from your homework. But it'll say find the values of C guaranteed by the mean value theorem for integrals for the function over the given interval. All right, so first of all, I'm going to write down what that theorem said. Remember, it said from a to b of my function, the integral of that has to equal f of c times b minus a. So when you see something like this, you need to kind of figure out what they want you to do. This left-hand side just tells me to find the integral from a to b of my function. So here's my function, here's my upper and lower limits. So I'm going to find this left-hand side first. So I have from 0 to 3 of x cubed dx. Okay, so I'm going to integrate that. When I integrate that, I get x to the 4th over 4, and I'm evaluating from 0 to 3. I'm going to plug my 3 in first, and then plug my 0 in. So 3 to the 4th over 4, that's going to give me 81 over 4. Okay, so this left-hand side is 81 over 4. And they said I can set that equal to f of c, so I'm just going to write f of c times b minus a. But I know what b minus a is. It's 3 minus 0, or 3. Now, if I want to solve for f of c, okay, I would have to divide by 3. So when I divide by 3, 81 fourths divided by 3 is going to give me 27 fourths. Now here's the deal. I can find out what f of c is. F of c, c is going to take the place of my x. So if I take the c and replace that in place of my x, I have 27 over 4 equals c cubed. And now I'm supposed to find out what c is. Find the value of c guaranteed by the mean value theorem. So if c cubed is this, I need to take the cube root of both sides. Okay, and when I put that in my calculator, it's approximately 1.889. And that makes sense. It has to fall between 0 and 3. So that's where that c value would lie, or if I drew a rectangle, it would give me the exact value of that interval. So C is 1.889. That's my answer. All right. Now that leads us up to a very important theorem, or a very important definition. Definition of the average value of a function on an interval. Okay, it says if f is integrable, so I can take the antiderivative, I can integrate it on the closed interval from a to b. You can find the average value of that function f by doing this equation. 1 over b minus a times the integral of that function from a to b. Okay, so here's what it's going to look like. There's just the definition again. I don't know why I had it twice. Find the average value of 3x squared minus 2x. So remember, here's the formula for average value. Okay, so I'm going to say 1 over b minus a. So 1 over 4 minus 1 times the integral from 1 to 4 of 3x squared minus 2x dx. So that's 1/3. Now I'm going to integrate this. 3x cubed over 3. So my 3's will cancel. That gives me x cubed minus 2x squared over 2. So that gives me x squared. And I'm evaluating from 1 to 4. Okay, so I'm going to plug my numbers in. 4 cubed minus 4 squared minus 1 cubed minus 1 squared. So remember, I still have this 1/3 out in front. 64 minus 16 minus 0. So that's 48 times 1/3, 16. The average value of that function is 16. Okay, let's do another one. Find the average value of cosine x on the interval from 0 to pi over 2. All right, so I know it's going to be 1 over b minus a, which is pi over 2 minus 0, times the integral from 0 to pi over 2 of cosine x dx. So this just looks weird. What is 1 divided by pi over 2? That's 1 times 2 over pi. So I'm going to rewrite this as 2 over pi times the integral of cosine. When I integrate cosine, I get sine x. And I need to evaluate from 0 to pi over 2. So I have sine of pi over 2 minus the sine of 0. So I have 2 over pi right here. What is the sine of pi over 2? Sine of pi over 2 is 1 minus the sine of 0, which is 0. So when I simplify that, my answer is 2 over pi. So the average value is 2 over pi. All right, so the first important thing, finding the average value of a function. Now, we've already had the fundamental theorem of calculus. Okay, this is the second part of the fundamental theorem of calculus. The first part was when we learned how to integrate and then just plug our numbers in for definite integrals. This is completely different. The second part of the fundamental theorem of calculus is going to look different, but it's actually really easy. It says if f is continuous on an open interval containing a, then for every x in the interval, remember what this stands for, d over dx is the derivative of the integral from a to x of f of t dt equals f of x. Now that sounds really confusing, okay, but it's actually really easy. It's kind of common sense. If I'm finding the derivative of an antiderivative, doesn't it make sense that I just end up with my original function? Here's what it looks like. And here are the rules. And first of all, this example 3, this is a typo. This is a 0 right here. So let's talk about the rules. First of all, the rule is I have to have a constant on the bottom. any constant number. Okay, so a constant on bottom, and then usually it's going to be some kind of variable or something up here at the top. All right, so look at example 3. I want to know the derivative of the antiderivative from 0 to x of this function. Now the reason this is t's, because they had to make it different. If this is an x, they just used t's here, okay, so that we would have different variables. So if I'm finding the derivative of the antiderivative and it follows the rule is it has to be a constant here and my variable is up here. Doesn't it make sense that it's just going to be this exact same function, but I'm going to plug this x in? So my answer is x squared plus 1. Oh, and it's the square root. Yes. Okay. That's easy. We like that. Let's look at another one. Find the derivative of this antiderivative. Okay. Well, I have a constant on bottom, so that's good. But my top is a variable raised to a power. All right, so the first thing I'm going to do is I'm going to substitute this in place of my t. So my answer is cosine x cubed. But the difference on this one, it was x cubed, and it has to be just an x there. So if it's anything other than just an x, I can substitute it in just like I would normally, but then I have to take the derivative of this function. So it's x cubed times the derivative of whatever that was. And the way that we'll write our answer, is that right there? That's my answer. Okay, I think we have one more, maybe two. Use the second fundamental theorem of calculus to find the derivative when I have this. Now this doesn't follow my rules. Okay, it has to be a constant on bottom and then my variable has to be on top. But let's think about this. If I were to graph this, 4t plus 1, that's just, I don't know, it crosses the y-axis at 1, it has a slope of 4, so we'll just say it looks something like this. It's linear. Okay, and I want to go from x to x plus 2. Well, let's just say this is x, and somewhere over here is x plus 2. Okay, and I'm actually finding the area under this from here to here. Well, I'm going to have to break this up. If I told you this is a geometry problem and I told you to find the area of that trapezoid, wouldn't you have to find the area from here to here first and then subtract this amount, right? I'd find all of this and then subtract the red part. So that's what I'm going to do. I'm going to break it up. I'm going to go from 0 to x plus 2 of 4t plus 1. And I'm going to subtract this part from 0 to x of 4t plus 1. Well, now this is something I can use the fundamental theorem of calculus for. I have a constant on bottom, my x is on top, so I just substitute my x plus 2 in place of my t's. So I have 4x plus 2 plus 1. This was something more than the x, so I would multiply by its derivative, but its derivative is just 1. Minus, this one I just plug in my my x, 4x plus 1. And I'm going to simplify. 4x plus 8 plus 1 minus 4x minus 1. My 4x's cancel, my 1's cancel, and my answer is 8. Okay? And then I'll answer any questions you have in class.